Origin and direction of magnetic fields. 1819. Hans Christian Ørsted was looking for a relationship between electricity and magnetism. He set up a current-carrying wire above a magnetized needle. So here's our wire up here, okay, carrying current. And here's the needle right here, compass needle. This is a drawing from a text by Augustin Privat de Chanel from 1876. I always like to show some historical things. And if you want to clip down at the bottom, you can see what a 19th century physics textbook looks like. When there is no current in the wire, the needle aligned with the magnetic field of the Earth and pointed north. So that's this picture right here, right there. We're pointing to the north, okay? That's where the needle starts. So let's erase that. When current was supplied, the magnetized needle rotated on the pivot and pointed at a right angle to the electric wire. The direction of this rotation would depend on the direction of the current. So that's this here. You can see the thing rotating. Okay, that's quite a surprise. Ørsted deduced that an electric current produced a magnetic field, and that affected the compass needle more strongly than the Earth's magnetic field, which is pretty amazing, right? This little current-carrying wire creates a greater magnetic field than the entire Earth. In addition to this first experimental evidence that electric and magnetic fields are related, which frankly is good enough, Ørsted also produced aluminum for the first time from a chemical reaction of aluminum chloride. Aluminum was actually used in the 1960s for household wiring in the US because why? It was cheaper than copper. It was later banned for household wiring as it would oxidize the connection points, which would increase its resistance, and it would heat up, sometimes melting and causing fires. Here's a picture of Hans Christian Ørsted, who actually knew Hans Christian Andersen, who wrote the kids' books. He was a physicist and chemist. And this first picture over here, there's no current in the wire, and all the compass needles are pointing in the same direction. They're pointing north. When a current is put on, you can now see the compass needles pointing in different directions, but always perpendicular to the wire. Right? If I were to draw a line out to one of these compass needles, you see that they're perpendicular to it, or tangent to that circle. Ørsted found that a current-carrying wire that actually had a live current in it would generate a magnetic field. But where does the Earth's magnetic field come from? Well, it's very similar to that of a bar magnet. It is caused by the circulation of molten iron alloys in the Earth's outer core. Just picture these molten alloys as having many, many, many free electrons that move together, and you now have a current. And as Ørsted demonstrated, currents create magnetic fields. And here's a picture of the Earth's magnetic field. And we have the North Geographic Pole, right? North of Alaska and Canada and Russia. And that's actually the South Magnetic Pole. Why? Because your compass needles, the north will point, you've got your little needle here. The north pole of that will point to the north. So if it's pointing to the north, what's attracting it? Well, the Earth's South Magnetic Pole. So the geographic poles and the geographic poles and the magnetic poles are opposite. Down below in Antarctica, you have a south geographic pole, but that's the north magnetic pole. The Earth's geographic north pole is a south magnetic pole, as the north ends of the magnets are attracted to it. The magnetic poles are not located on the Earth's axis of rotation. So if the Earth is rotating on this axis, the magnetic poles are slightly off. The magnetic field extends from the core to the outer limits of the atmosphere. That's called the magnetosphere. This picture, not to scale, of course, right, because here's the sun and here's the Earth. This shows the interaction of the solar wind. The electrons, protons, alpha particles, heavy ions, and atomic nuclei that are shot out from the sun all the time with the Earth's magnetosphere, which is in blue. The magnetosphere protects life on Earth from being subjected to this ionizing radiation that would cause great harm, and that's an understatement. Many of the particles in the solar wind are prevented from entering the lower reaches of the Earth's atmosphere by the magnetosphere. Some particles enter the magnetosphere and are directed along the magnetic field lines to the magnetic north and south poles, That's where the fields are the strongest. As they go through the atmosphere, they collide with oxygen and nitrogen atoms, transferring their energy to excite those atoms. They then give off this energy in the form of light. The kinetic energy to light energy transformation that occurs in the Earth's atmosphere, right? Because if you excite an atom, you kick the electrons up in orbits, they then decay back down to the lower orbits, and they give off light. So this produces the Aurora Borealis and the Aurora Australis. The Aurora Borealis is shown from space encircling the south magnetic pole, which of course is the geographic North Pole. You can see there's Greenland, there's the Arctic ice flows. It's kind of a cool picture. Another name for the Aurora Borealis is the Northern Lights.